Hi guys, as part of today's lecture we will look at how can we control the intensity of the LED using a PWM component. So we will look at the PWM component in the PSoC creator software, and using the concepts that we learned in the previous lecture about PWM, we will write the program to vary the intensity of the LED. So before we move on to the PSoC creator software, let us first understand a few basics. As we know that the LED has two terminals, an anode and a cathode, and as we also know that on board the PSoC 4 Pioneer kit we have the LED connected such that the anode is shorted to VDD and this is connected to the PSoC device. So that said, how do we vary the intensity using PWM? Well, if I have a PWM signal looking like this, such that which is close to, let's say, 80% duty cycle, 80%, and if I give it across an RC circuit, so the output here would look something like charge, and if I do this fast enough, then I see an average value which would look like a DC value. Again, the condition is as long as this case, and this case is happening fast enough. Similarly, if I have a PWM signal which is like this, the output here would be smaller, so the average value would be lesser compared to this one. So basically my LED can be treated as an RLC circuit. So the principle behind varying the intensity is this. Now in my PSoC creator PWM component, I have the compare register, so I will change the value in the compare register using the write compare API, and by changing this compare register I will change my duty cycle, which is my on time, hence change the width of my pulse, and hence I should be able to vary the intensity of my LED. I hope this basic concept is clear. Then that said, let's go ahead and write a program which will slowly increase the intensity of my LED and then fall down, again increase. So this is what we call as a breathing LED. So let's try and implement this using the PSoC chip. So let's go ahead and start a new project. empty PSoC 4 design because we're doing it using the Pioneer board, which has the PSoC 4 device. So let's name this as lab 3 underscore PWM LED and go ahead and click on OK. So our step number 1 was that we selected the target device. Step number 2 was selecting the components. Now here we do have a component, a few rather. So let's go ahead and get the PWM component first. Then let's go ahead and we will need a clock for the PWM component and reset. So let's go ahead and get the clock. The clock can be found in system. So drag and drop the clock component. Then we will need, since we are not going to reset this anytime, we will connect the reset to logic low, which is 0. And then we will need one PWM output. Since we are connecting this to an LED, we will need a pin which will be a digital output pin. So these are the components and my pins. So let's start configuring them. First of all, let's look at the PWM. Now, since I'm going to control the duty cycle using software and I am using only one output, I will let this compare value be at 127. This 127 value means that when I start the PWM component, this is the default value, and then I can change the compare value using an API, which is the write compare value. If you look here, which is PWM underscore write compare, using this API we will be able to change the duty cycle, which is the width of the pulse. And again, let's keep this in 8 bits. Let's change the name to PWM and let's keep it the same. Okay, now my clock, I can choose the frequency I want. Now if my frequency is 12 megahertz, then the PWM period here will be 12 megahertz divided by 256. So I hope you understand that the total period of this PWM from here to here will be the clock frequency here, 12 megahertz, divided by 256, because the total time taken from here to here will be governed by this frequency. So you can keep it at 12 megahertz. Let's name this as CLK just to keep it short. Again, if you would like to understand the clock component, you are free to go ahead and read the data sheet. We will keep this at 12 megahertz. Go ahead and click on OK. Now, if you remember that I said that a output pin can be controlled either using a microcontroller, which is the software component, or you could program it using a hardware connection. Now, since the output of this digital pin is governed by my PWM, hence I have to keep it as a hardware connection. Since now I am not using an API, I am rather driving this pin using a hardware component. So let's name this as LED R since I'm controlling the red LED. So go ahead and click on OK. Now we have to connect these components. So click on the wire tool here, and when you place it on the component, it turns X from a plus sign. Left click and left click at the destination. Similarly, left click, left click. Now you can also use the shortcut W, left click and left click. Now TC stands for terminal count and interrupt is interrupt. So only if you're using these terminals you can actually connect them up to something else, otherwise you're free to let this be. So the components have been connected, so we've done the connections. Now we have to map this LED pin to a physical pin. So the red port is P16, which is LED R. So we've finished the next step, which is mapping the design pins to the physical pins. Now let's go ahead and do the programming. Since we are not using any APIs for the pins, in this lab I am not including cypins.h. In the previous labs, since we used APIs for the pins, we did use cypins.h. Here I'm not. I'm going to say int I equal to 0. Now let's look at that API function a little more closely, which is write compare. So if you're using an 8-bit counter, then you have to give it a uint8 value. If you're using a 16-bit counter, then you give it a uint16. So here int I will be uint8i, and I've initialized this to 0. Now in my main function I will say PWM underscore start, which enables my PWM component. Then I do CLK underscore start, which starts my clock component. If you forget this step, then your PWM component or your clock component will not be turned on, and effectively your design is sitting like a dead duck doing nothing. So make sure you always start the components that you are using. So now for the infinite loop, in this case I can replace the for with also a while 1. So let's try the while 1 this time. So I'm going to write 2 for loops, one for increasing the compare value and one for decreasing. So I say for I is equal to 0, I less than 255, I plus plus, and then I say PWM underscore write compare I. Then I put a delay of 10 milliseconds so that I can see the intensity change for my LED. Then this is the increase in my set compare value, Now I write a similar for loop for decreasing my set compare value. So if I is equal to, for I is equal to 255, I greater than 0, I minus minus. So now from 255 I'm going down to 0 with a delay of 10 milliseconds. I'm setting my PWM width starting from 0, then going up and then coming down. Now whether your PWM is increasing or decreasing will depend on a few factors. Now one of those factors is whether you have a less than or greater than. In our case, since it is less, if your compare value is 0, then it's absolutely 0. As the compare value increases, your pulse width also increases. If you see, as I'm increasing my pulse width, so I hope that is clear, that depending on whether it's a less or greater, this for loop will increase or decrease your pulse width. So again, you have to be careful as to what the configuration is. That said, I think the program is ready to be built, so go ahead and build the lab. So once you get the rebuild succeeded, then we would go ahead and program the board. So let's go ahead and click on program. So now let's keep an eye on the board here. Now you see that the intensity is going down, it's coming up, it's going down, again it's coming up, it's going down, it's coming up. So we have a total of 255 cycles multiplied by 10 milliseconds. So it's taking roughly 2.5 seconds for the entire intensity to go up and come down. Let's make this a little faster. Let's give it a 5 millisecond delay and 5 millisecond just to increase the speed. Let's go ahead and program this again. As you see that the speed of brightness has increased. So now you can see that we can actually vary the intensity of this LED using the write compare API, with which we are actually varying the width of the pulse. So you can try as part of this lab to actually use this PWM in a 2 output mode, such that one output is given to the red LED and the other output is given to, let's say, the blue LED, and you can observe the changes on what happens there. So as part of this lab, we understood how to use the PWM component in the PSoC device. So in the next lab, we will look at how to interface a 7-segment display with the PSoC chip. I hope this lab was clear. Thank you.